What's up, guys? It's Misha. I'm recording my very first video on YouTube, and here's why. I've been a teaching assistant for a few years at one US university, conducting labs and discussion classes, mostly for EE students. One day after the discussion class, I talked to students about some problems we discussed in the class, and they asked me, Misha, why don't you make video on YouTube? We'll learn a lot from your discussion classes. And I thought, really, why don't I do this? I like teaching, I have some experience in it, I have camera, iPad, laptop, basically everything to record and post a video. Okay, let's try, I told myself, and here I am, and welcome to Meet class. Today, I'm going to solve a problem from the final exam in network analysis class. Students were asked to set up a matrix using the mesh analysis approach. The problem was given as a challenging extra credit problem. Well, let's solve it and see how challenging it was. This is a circuit that was given on the exam. What we can see straight away that it has three loops. Two small loops, the loop where the current I1 flows, a small loop where the current I2 flows, and the big one, the big loop where the current I3 flows. It means that our answer must have 3 by 3 impedance matrix. Let's draw it here. Multiply by current vector that has loop currents I1, I2, and I3, and it must be equal some voltage vector. What else we can see in this circuit? We have a bunch of transformers and mutually coupled inductors. We have two transformers that connect loop 2 and loop 3. We have two transformers that connect loop 1 and loop 3. We have inductor in the middle that mutually coupled with inductors in outer loop, L1, L2, L3, and L4. To solve this problem, you can start writing mesh equations right away, or you can do decoupling first. I will follow the second approach. I'll do decoupling because I believe there is less chance to make a mistake with voltage polarity. Now on the right side you can see the coupling circuit where the effect of the mutual coupling is represented by dependent voltage sources. The polarity of the voltage source is defined based on the current direction through the inductors and dot arrangement. When you do mesh analysis, you need to write KVL equations, and before we start doing it, let's label transformer voltages because we must have them in our equation. Let's take polarity according to the dot arrangement, say it will be plus minus, and label it V1 primary, V1 secondary. And we do the same for all other transformers. Now, as I have all voltage labeled, I'll write KVL equations. I start from loop 1, and when I go from minus to plus, I'll write this voltage with negative sign. When I go from plus to minus, I write this voltage with positive sign. Okay, let's do it. And the same principle for the second loop. And for the third loop. And now you have three equations, and it looks like you're ready to set up a matrix, but not yet. And why? Because you have transformer voltages in the equations, and they are not given. Your final matrix must have only given values and loop current so that you are able to solve the matrix. And now we have to use property of the ideal transformers to write the equations for primary and secondary voltage. V1 primary over V1 secondary must be 2 to 1, And this is true for all other transformers because they have the same turns ratio. And now you can write the third equation in terms of secondary voltage and take secondary voltages from the first and the second equation and substitute it into the third equation. Okay, let's do it, and I'll write the answer with collected coefficients. And now we have just one equation, and the question is where to take the other two, and they go from the property of the ideal transformer. For the first and the second transformer, we can write that I3 over I2 must be minus 1 over 2, and for the third and the fourth transformer, we can write that I3 over I1 must be 1 over 2. And these are our two equations, so that we have to have in the final answer in a matrix form. I redraw all the equations I need on this page, and I labeled coefficient for I1 as Z1, for I2 as Z2, and for I3 as Z3, and I reorganized current equations for transformer so that it can be easily converted to a matrix form. And now we have everything to write the final answer. We have an impedance matrix with Z1, Z2, and D3 in the first row, 0, 1, and 2 in the second row, and minus 1, 0, and 2 in the third row. This matrix is multiplied by current vector with I1, I2, and I3, and it equals the voltage vector that has V, 0, and 0. And this is your final answer. Was this problem challenging for you? It might look challenging in the first class, but when you inspect the circuit and do analysis step by step, it becomes relatively simple. Personally, I think that the problem can be a little bit more complex. As you notice, the transformers are connected in series and it blocks their flexibility because in this case they must have the same turns ratio and dot arrangement. I would add some connection between the transformers. And you know what? At the end of the video, I'll give you a problem to practice. Find the answers and leave them in the comment below. If you like this video, hit the like button, share it with your friends and subscribe to my channel. It was Misha. Thanks for watching me. Bye.